in the center of the object.
All right, so we've got this force due to gravity. Should not do W there.
And then same force going out of the object towards the satellite.
All right, so say F, Tom, gravitational force done. What else?
Nothing.
Yeah, that's,
All right, so in this respect, this is an incredibly simple problem, the fact that I have only one force acting on the object. Now, there's some thoughts occasionally from students that, doesn't that mean the satellite's gonna crash into the central object? No. There was I cannot remember which book it was. It might have been either for some reason I'm thinking it's the Phantom Tollbooth, sort of kids book,
Yeah.
where someone flies by throwing themselves at the ground and missing. And that's in essence what's going on here. The satellite's constantly falling, but it keeps missing. Illustrate that a little bit more, and then we'll get back to that problem. If I shoot something off the top of a cliff horizontally, what's gonna happen?
It's gonna fall
Fall out.
eventually.
Yeah. If I shoot it faster,
Maybe it'll
it'll
fall
still
farther.
fall. Yeah.
fall farther.
It'll fall slower.
It'll land further from the cliff. or-
Yeah, that's
What
probably
she
better
said.
word. I think you could have
Same
drawn
thing.
it, it was just the wording. And so on. If I keep shooting it faster and faster, it's gonna go farther and farther. Now, I got my mesa right here, and I got my projectile launcher, and I'm shooting it. At some point, as it falls, it's obviously going to fall in a curve. If I shoot it faster and faster, the curve of the planet or planetoid or whatever it happens to be starts to have an effect on how far it's going to go. Because we generally assume flat Earth under most situations, but the reality is Earth's not flat, despite what some people are telling you. And if you shoot it fast enough, it's going to come back around and smack in the back of the head. So this makes it a satellite. This is orbit. It's constantly falling, but just keeps missing. So that's what's happening here. That's what's happening with the sun, and what's happening with the moon around the Earth. So direction of acceleration for the satellite,
Towards the central object.
or with confidence.
Towards the central object.
There we go.
Thank you.
Therefore, what kind of acceleration is this?
Centrifugal.
Yep. Working my way through the process. Therefore, our coordinate system, our coordinate axes, I'm just going to make this way positive. Do we need to decompose that vector?
Yes.
No.
So I got a yes and a no.
We
And
don't have.
fight.
You.
We don't have to. We could the way it's drawn, it's
Yeah.
not. I think it would
It just
be
goes straight in
more
one direction.
difficult if we decomposed it. So it would be best if we didn't.
Yeah, it would be best. I'm trying to figure out, Brooke, what you're thinking about. Is it the fact that those aren't perfectly
It's-
parallel?
Yeah, it's just, never
Oh.
mind. Yeah, it's fine.
Okay. They're supposed to be parallel, and I'm assuming in your own notes you would draw that properly. Equation of motion. So we're plugging in F equals ma. How many equations of motion will we have for the satellite?
Just one.
So we have F sub g is equal to the mass of the satellite times A sub c. And now substitution. We have a formula for A sub c, and we have a formula for F sub g. So big G, mass of satellite, mass of central object, over the orbital radius squared is equal to mass of satellite times v squared over. I didn't mention this before, but let's take just a moment to talk about what R means. in the gravitational force formula, see, this is the second floor, so this is, I'm about, let's say 10 feet above the ground. What is R? For the gravitational force between me and the earth, what is R?
5? No. Is it?
It would be 10, wouldn't it? Because that's like the halfway, it's the radius between you and the earth, and presumably there's more on the other side.
I thought I heard contradictory things there. Say it again, Ian.
It's the distance between you and the large mass.
Right.
So that's your radius, because if you were to track a circle around the middle of the earth, you would form a circle with a radius of 10. Or around the point that or the point of the ground, I guess. Unless we.
All right, so you're going for 10 feet is R?
Yeah.
And you were originally said 5, but then you weren't quite sure that made
Yeah.
sense.
I'm convinced with what he said.
So you're going with Ian?
Yeah.
Anyone want to stand up and just go, come on, guys. What were you thinking?
Do we have to work with center of masses?
Yeah, I was thinking it would be the closest part of the object,
But that's not
but I'm
necessarily.
not sure, yeah,
accurate
like if
for
it's the
gravity.
Earth and the Sun, is it the distance between the center of each of those, or like the closest?
Yeah.
I mean, at that scale, it's hard to tell.
Yeah, because if you're counting the center of the mass, then it's the radius of the Earth plus 10.
Yeah.
All right, so let's see if we can come up with some way of figuring out if it is 10 feet or bigger. So let's just say that R is the distance from the surface to surface distance. So what would happen to this fraction as I move down? As I go down the steps, what happens to this fraction?
It gets smaller.
Okay. So what happens when R is 0?
And
It
you're
doesn't
breaking the
exist.
rules.
Suppose let's make it a small number then. Suppose R is, because mass of the Earth is on the order of 10 to the 24th
Yeah.
kilograms. My mass is on the order of 10 to the 2nd kilogram. G's got a 10 to the negative 11th, but still that 10 to the 24th seem rather dominant. And if I'm 1 meter above the ground, then this becomes
1.
10 to the negative 11th times 10 to the 2nd times 10 to the 24th times whatever the coefficients are,
Yeah.
which is huge.
You die.
Yeah, basically our bodies are not designed for that. So it doesn't make sense if R goes to 0, this thing shoots up to an incredibly huge number, which means that if you touch the ground, you would never be able to pull off of it. Matter of fact, the blood would suddenly get pulled to whatever's touching the ground,
Yeah.
and then the blood would just basically get pulled out. It is indeed center to center. Because what's happening is, let's go over here, a person standing on the planet, you're actually being pulled through every tiny little bit of mass on the planet. And ultimately, you can work through the calculus of it, it ends up being center of mass. So it's center of mass to center of mass distance. So R here, the R on the left-hand side is the center of mass to center of mass distance. The R on the right-hand side is the orbital radius, which happens to be the same thing in this case. Which is fortunate because I used the same letter. So technically, this is orbital radius. And this is center of mass to center of mass distance. Center of mass 1 to center of mass 2 distance.
So what if it wasn't, would that just deal with ellipses then? Like the orbital radius being not the same as the center of mass to center of mass distance?
let's hold off on the elliptical for right now.
Okay.
I want to address some of it,
Yeah.
and then you ask your question again if I don't answer it.
You're good.
I'm trying to think of a situation where, because if the center of mass of the Earth were, say, here,
Oh,
then the orbit probably would develop around that spot right there.
yeah.
Something more like that.
Isn't that kind of like how the moon orbits around Earth? Because we have supermoons and stuff like that.
I don't know. All right, so now let's simplify it some. Mass of the satellite cancels out. So really, just as we've done with so many other things, if I take an object and I drop it, the mass of the object does not affect the acceleration in a nice ideal world. And I will tell you, there is no air resistance that a satellite in orbit is going to be feeling. One of the R's will cancel out. So what I'm left with is G times the mass of the central object over R is equal to the speed of the object squared, speed of the satellite. So if we flash back to the lab, you have some distance r here of a circular orbit traveling at some speed v. I know that that is equal to distance over time. The distance is 2 pi r, just the circumference of the circle, divided by the period. Capital T for period again. So what's the period of the Earth going around the sun?
Beats me.
Oh, you know it.
365 days.
Yep. Strangely, people usually go for that first instead of just saying 1 year. But, yeah,
Yeah, I was gonna ask, do you use like a year? Do you use months? Do you use?
yeah, there are a lot of answers.
Okay.
52 weeks.
Yeah, like.
And change. All right, so this is equal to 2 pi r over t squared. Go ahead and squaring it out, I'm left with g times the mass of the central object over the orbital radius, or center to center radius, since they're the same in this case, is equal to 4 pi, oops, that's not a 2 there, that should be a c. 4 pi squared r squared over t squared. And so now I've got g, mass of the central object, over 4 pi squared, and the reason I'm doing this is I know where I'm heading on it. Multiply both sides by r, and I end up with r cubed over t squared. The only restrictions I've done in this problem so far is I assume circular orbit. And I assume that the overwhelming gravitational force acting on any satellite is from the central object. If I had 2 satellites, I'm not worried about the gravitational pull between the 2 satellites. So for Earth, this is 1.5 times 10 to the 11th meters cubed, divided by the period of, let's get this down into seconds. So the period of Earth is 365.25, rounding off to two figures, days, times 24 hours per day, times 3,600 seconds per hour. So how many seconds?
31,557,600.
31,567,000.
600. No, I'm sorry, 76. 576.
That?
No.
There's
Change
two fives?
Change the second 5 to 6. Second 5. Let me read it off again. I screwed up.
Apparently I did too.
It's 31557600.
All right, and that was 31 million, so 10 to the 7th.
Yeah.
Anyone else get the same thing? Or we're just trusting them?
Yeah,
Well, I was trusting.
Okay, but you,
I got it, yeah.
Okay. over 3.1556 times 10 to the 7th squared. And what do we get?
We got 3.39 times 10 to the 18th.
Units?
What are we solving for? Is this? Okay, so it's meters per second.
Is it meters per second?
Yes, meters per second. Is that
No.
Is that not the S you just wrote it down?
It is an S right there.
Oh, yeah, it's, meters cubed per second squared.
Yes. This is no particular number other than it works with that over there. We can actually then find the mass of our central object using this, because we have this value right here. So if we multiply times 4 pi squared and divide by g, so if we take that times 4 pi squared divided by 6.67 times 10 to the negative 11th, I'm gonna guess we get somewhere around 2 times 10 to the 30th. Still right. Let's just see how close we get.
We're multiplying the 3.39.
Times 10 to the 18th times 4 pi squared,
And then dividing all that by
big G.
big G. Got
Please come out right.
it. 2.0064 7 times 10 to the 30th. So, yeah, something like that.
So we have a pretty good idea of what the mass of the sun is. Also looking at satellites going around the Earth, we can find the mass of the Earth. We can find the mass of any central object. Doesn't help us find the mass of the satellite unless something's going around it. Suppose instead, questions before I expand this? Yeah,
How did you get the T?
how do I get that too?
How did you find the 3.15576 and 0?
That's so big T is the period. It's how long it takes for something to go around, the satellite to go around the central object. So for Earth going around the sun, that's the number of days in a year. And then I convert it into seconds. So that's where that number comes from. It's the number of seconds.
N 0, 7? 6 N?
It's
Sorry.
times 10.
That's times 10 to the 7th.
Okay. I thought it was N 0.
Oh, no. Sorry, got sloppy. Other questions? Poison?
Yeah, why did we raise the R to the third power?
Because I have R squared here. I wanted to get the R's and T's on one side and everything else on the other. There's a reason for that, which I haven't really revealed yet, but there's a reason I did that. So I multiplied both sides by R to get rid of this one. So I had already had an R squared here. When I multiplied by R, it becomes R cubed.
Oh,
Okay, so we solved for velocity,
No, speed.
the speed, sorry. But we didn't square it. Where did the velocity or the speed squared go?
So speed is 2 pi R over T.
Gotcha.
Oh, and then I squared it. That's where the 4
Gotcha.
pi squared
Okay.
R squared comes from.
So we solved for velocity and then we plugged the velocity into the equation to get the mass?
We plugged it into, so we got this generic equation right here.
Yep.
And then we plugged in these numbers in order to find mass of the central object, sun in this particular example.
Okay,
And speed, not velocity.
gotcha. Okay.
Any other questions? So if we take our sun as a central object, and I look at Mars going around the sun, if I took the radius, the orbital radius of Mars, and then the amount of time it takes to go around, so I take an orbital radius, I cube it, I take the amount of time it takes for Mars to go around the sun, square that, what am I gonna get for Mars?
I have no clue.
Can you say that again?
So I'm gonna take so just talking about Mars now, going around the sun. I take the orbital radius of Mars, cube that. I take the time it takes for Mars to go around the sun, in seconds, to make it convenient, in seconds, square that, and divide. That orbital radius cubed divided by the time it takes to go around the sun in seconds, squared, what would I get? No.
The mass.
No. Just looking for an actual number.
That's what I was saying, I don't know. Well, we could put the speed of, no, we could put the mass of the sun into our equation and then use 4 pi squared times that, but we'd have to solve for time.
Oh, you're making it way more complicated than it needs to be.
Really?
Yes.
Okay.
Radius?
Looking for a number.
Is it an integer?
No.
Pod.
That was a good guess.
The gravitational constant times the mass.
Still quite complicated.
You're like genuinely just looking for a number, like
Yes.
it's not.
I'll look for a number of that ratio.
Oh, 1 year.
No, that,
Got it.
I'm very lost.
alright. Notice I did not tell you what the orbital radius of Mars is, nor did I tell you how long it takes for Mars to go around the sun. So, that I'm hoping is, I'm not expecting you to know that information off the top of your head and then work out on a calculator. We've already done the hard work, actually.